Welcome, everyone. I'm your first presenter. I'm Jacob Rice, for those who don't know me, and I'm going to be presenting today on custom views for people who aren't Eric Niebler. So this is not intended to be an introduction for why views are useful. Instead, I'm going to assume you know a little bit about them, and I'm going to just show how I made one for myself and the process of learning what goes into one. Okay, so I think it's safe to say that we're all very excited about views. They allow for this really nice, clean, composable, lazily evaluated syntax. It's all very handy. We've seen a lot of this in different YouTube videos and everything, so I'm going to assume that we're somewhat familiar. But as always with a new feature, I'm most excited about implementing one myself. The STL is not complete, and it never claims to be complete. It's supposed to be extended. So it's important that we can extend these things very easily. The problem is they can be a little bit daunting. This is the MSVC implementation of filter view, which I thought would be the simplest view other than like all. That it's 265 lines. That's a lot. Eric Niebler's in range v3 is 100 lines, but that's because it uses all this shared code and hides a bunch of detail. So that doesn't really make it more readable. So where do we start? How do we figure out what goes into making a view? As always, I think it's best to start with an example. So this is just a little toy project that I have been playing around with. It's playing with orbits in a solar system. And these are the concepts that I'm using. So I have a gravitational body, which is just anything with mass, location, and velocity, and gravitational range, which is just a range of gravitational bodies. Let's look at how I calculate the gravity that is affecting this red planet. In update gravity, I'm passing in the red planet and a list of all of the gravitational bodies, and then a delta time for whatever step I want, maybe between frames, whatever. So I calculate the force, and then I get acceleration, and I update my velocity and location through that. And in get force on body, we're doing a transform reduce for this, because we're essentially taking all of the gravitational bodies and transforming them into a vector of the force that is being applied on the red planet. And in this line, we are saying that when we run into the red planet in the list, we'll just say it exerts 0 force on itself. It's fine for a video game. But this still feels a little bit weird to me, because it's weird that I'm walking through the entire list every time, and every single time I'm skipping one, right? What I really want to be doing is taking my list of gravitational bodies and viewing it as groups of pairs, so that I can easily see each body paired with everything that exerts a force on it, right? I could do this with a Cartesian product view, which is implemented in range v3, and then a filter view to remove pairs of matching elements, and then maybe a chunk view to group them, but that's too much. So I'm going to implement this for myself. So first we need to go over what is a view. Okay, I want to disambiguate a little bit here, because ranges are not a new idea in C++20, but the formal definition kind of is. It's a generalization, right? A range is a collection of things. So this includes standard containers, and it's just anything with a begin and an end. And this is the entire concept. A view is a specific type of range, and most importantly, it's constant time, copyable, movable, and assignable. That's what sets a view apart. But what actually goes into one? How do we make sure that no matter how many elements are behind this view, it's always this like lightweight thing that we can use? This is essentially the definition of all pairs view, which is what I'm calling the one that I showed previously. There's a lot hidden in this line, but really all we're doing is we're taking a view in of some template type, and then we're providing a begin and an end. But that's actually hiding a lot. And this is my suspicion, that a view is often just a supplier of a very fancy iterator. And that's certainly true in this case and most of the other ones that I've seen. So just to go over a little bit of context, I'm going to be referring to the group of yellow paired with everything else, this bracketed section, as the inner view, and then the iteration across those inner views as the outer iterator. This is really what the definition is for the all pairs view. I've split up my classes, my internal classes, and I have an inner iterator in Sentinel. I'm going to skip over why I did the Sentinel. We can talk about that later if you want. And an inner view which supplies those iterators, and then an outer iterator which supplies the inner view. Inner iterator does most of the work. For example, it has a value type of pairs where its reference type is a pair of references to gravitational bodies, as we kind of saw before. And then these are its members. It's not a lightweight iterator. It has 3 members, iterators, which is, you can optimize that. It doesn't really matter. But I'm just doing forward iteration for right now. So this is really all I have to provide. To go into it a little, this is really the only interesting logic, but it's not even interesting. This just is the case where when our outer iterator or inner iterator reaches the same element as our outer one, we want to just bump right past that because we don't want to supply pairs of matching elements. Here's the constructor, and we make sure that we correct our inner iterator, and our dereference operator is the pair that we talked about before. And then our increment and equality are both very straightforward. Skipping over the Sentinel. Here's the inner view. This is actually the whole definition of the inner view. It's not technically like a useful view, but because it's an internal one, it doesn't really have to be fully defined, but all it does is supply a beginning and end. And that's all it needs. And then our outer iterator is easy, it's simpler than the inner one. You know, it has, there's some hand waving here. I'm being lazy because it's slide code. To do this properly, we would have to be using proxy iterators because we're doing a value type thing and it gets weird, but I'm skipping that. So then our dereference is an inner view, as we said, and that inner view is created with the current outer iterator. And that's it. So that's our whole all pairs view, right? That's the entire definition. There's our begin and end. But what about the piping operator? Because that's actually one of the coolest parts of views, right? This is the normal structure for how a piping operator works. I just showed you the all pairs view. In the standard, this would be like filter view. There is a private unspecified class. The convention is to have the FN suffix. And that is what provides the composition and piping operation kind of thing. And that'll inherit from something which does this generally, and then you have your specific version for all pairs. And then there's a public instance of this, a global instance, and that's what you put into pipelines, so like filter. Here's my implementation. So essentially, I have a basic concept, and then my all pairs function takes a range and returns an all pairs view that wraps that range. And then I have my global instance. Some of you might be ahead of me and you might have noticed this horrible thing that I'm doing, which is inheriting from a private MSVC class that I'm not supposed to be touching. The reason I did this is because, well, frankly, it was Tuesday by the time I realized I didn't do the piping mechanism, and I didn't have time. And because it's kind of hard to get right. This is another MSVC thing. This is their whole pipeline. And you can do it on your own. It's not that bad, but it's hard to get it perfect. And so it doesn't really make sense to write it for yourself. So don't do this yourself. Don't inherit in production from a private, MSVC class or whatever platform you're on. Instead, you should use something stable, one that you implement yourself or something open source. I believe Range v3's make view closure is stable. It's in the documentation, but it's not documented. It's just named. So I'm not really sure if you're allowed to use that or not, but if you know, please tell me. So just a couple of closing tips for learning on your own. One, test-driven design is always the best idea, but especially here, views are really easy to use. So just start with your use case and just write enough code to fill in the gaps and get your view to work. And two, Range v3 may not be the best starting point, especially when you're starting to learn. There's a lot of, it's really easy to write when you're in that context, but there's so much hidden code and all these macros and all these crazy things. it's funny to say that MSBC's STL is easy to read because it's never easy to read, but it is actually useful to see something that's that in line. So that's just my 2 cents. Here are some things that I skipped over because I didn't have enough time to do it properly, but I'm not really going to talk about them. So that's all I had. Thanks.
Awesome. Thanks, Jacob.
Yeah.
Appreciate that. So while Deane is getting set up, does anybody have any questions of Jacob?
I just feel like I want to say that you said this is a lightning talk, but really it seems like it should have been like a 4-hour presentation on what exactly, because you're like, I mean, hand wave, it's fine, just inherit from the private thing.
Yeah, so I didn't know how to make a view when I committed to this being my topic. So I learned. Yeah, I could easily make a nice hour-long talk that gets into proxy iterators and all of that stuff. Those have been beaten to death over the years. It seems like if you're interested in those, then you've probably learned at this point, or you can find papers on them and all of that. So I didn't really feel that need, but the piping mechanism, that one was a stumbling block.
Yeah, if you're willing to, Jacob, I think that would be an awesome full-blown, like presentation later in the year sometime.
Yeah, absolutely. I would
as early as January, February, March, whenever you're comfortable doing it.
As early as next month.
Hey, he's already got all the material. It's fresh in his head, right?
Yeah.
So like we don't want to wait. So.
It did take me a while to cut it down to 10 minutes, so I could just
right?
Put back the original content.
Yeah, there you go. There you go. Awesome.
Yeah,
Thank
I'd love
you.
to.
I have one question and a couple comments. So fantastic.
Gets the JetBrains license.
Oh, that was unintentional. But I'll take it. So what was the bad name that you had? It was like unique self Cartesian product or something like that. Was that it?
Yeah.
So when you had that on your slide, it actually made me realize that I've been talking about a function that doesn't exist called triangle product, which is basically Cartesian product, but it only takes like the upper triangular matrix of like the combinations. And I don't know why I haven't noticed this until now, but like that's what you're explaining. It's based like
you need upper and lower though.
No,
is it not?
Yeah. So I think what Jacob presented was the matrix without the diagonal.
Oh,
right. Whereas
you need
a
a
triangle product, if you have a commutative operation, then yes, you can only use one half. Either half doesn't matter.
Okay, so this was basically like Cartesian. Yeah, it's a flattened outer product without the diagonal.
Right. Or, in other words, all pairs.
Yeah, like I was looking for it. I know that there's a language that has an actual algorithm called every pair, which I think like that's the thing is I'm not sure which versions like actually have like is 1, 2 and 2, 1 are those both included? Like I'm sure that there's one where it excludes it. But I looked it up. I found all pairs from R. But anyway, this is like you've totally like upended. Like I've been saying, oh, triangle product doesn't exist, but like I'm sure that there's a language that has a version of all pairs that it's like order doesn't matter, just give me the unique combinations, which wouldn't exactly be triangle product. I think
normally, I think normally you do that with a list comprehension.
Yeah.
Right.
Yeah, it would be really easy
in Python or in Haskell, which is just the applicative instance on lists.
Right.
So
anyways, I'll have to do some more research. My second comment is I'm not an implementer of any of the ranges libraries. So like if Tristan or Eric or Casey or any of them were here, they'd be able to comprehensively like make an informed statement. But from my like attending the meetings, I'm pretty sure, although you may be able to define like the pipe operator for your own views and adapters, you can't actually hook into like the standard library facility, which is something that they're working on for C++ 23. It's like considered the top priority because currently like there's no way to use both ranges v3 and like the standard ranges together because you can't hook into that. There's no type trait or anything to hook into the pipe operator. So like I am not completely sure, but like the trick you might have done might be like currently the only way if you want to do like a, stood views filter and then your custom view. Like that actually might be the only way to do it, like something sort of that's cheating.
That's interesting. That's not the impression I got just from reading the MSVC code, but I'm not sure whether that's standard. Like it might not be defined in the standard that way. But the MSVC stuff looked like it could just take anything that was composable, and it was just this very generic template with concepts that didn't require their type to be used, but I'm not positive. So I'll definitely look into that though.
Yeah, maybe when this is on YouTube, we'll ping one of the experts and ask them.
Yeah.
There you go. I like it. Awesome. All right, Ben, are you ready to go?
I am ready, but I have a question for Connor briefly. Triangle product, did you use that for day one of Advent of Code?
No, I used
because that's what I wanted it for.
yeah, I used outer product and APL, and then when I was actually competing to solve it, I used a function called combinations from Python.
Okay. All right. Well, with that, I'll go ahead with my lightning talk. I'm sharing correctly. Yes. So I just wanted to surface a few things I discovered recently about concepts and subsumption, and illuminate a few things about how to constrain function overloads with concepts. So, oops, my clicker isn't on. I have a very loud keyboard, so I'm using a clicker to save you. So concepts are morally equivalent to type traits. In terms of constraining functions, we use them in much the same way. They have better they're better characteristics, but these things are basically saying morally the same kind of thing. The concept also checks the return type, which is generally easier to make that return type check. So that's kind of the setup. So where type traits, typically we'd inherit from true type or false type, and we'd have a corresponding _v that's context for a bool. Concepts, at least where I've seen them, usually issue the Hungarian kind of _t_v that we might use. They can be implemented in terms of each other. Of course, not this slide won't compile because it's kind of recursively in terms of each other. But if you have a concept, you can implement type traits in terms of it like this. And if you have a type trait, you can implement concepts in terms of it. Concepts don't completely replace type traits because you can't pass concepts around as template arguments. So there are cases where you will still need type traits. And of course, as we know, they do a lot more than type traits, all of these things. The last bullet point here is really what I want to talk about, how to combine concepts. So if we have a shape class, a hallowed shape class, we could make some shape concepts to constrain various kinds of shapes. A basic shape might just have an area. A more advanced shape might have a perimeter as well as the area. And we might be tempted to write it like this. So you can see the basic shape just says, does it have an area? And does that area function return a size t? Okay. And then to be a shape, you need to be a basic shape and you need to have a perimeter function. So let's say we defined it like that. And then we start to make some shape classes. So we have a rectangle. Rectangle has area and perimeter, and it fulfills both concepts. And we have an ellipse, which only has an area, and calculating a perimeter of an ellipse turns out to be difficult, so we leave that out. And an ellipse is a basic shape. So this all compiles fine. These shapes fulfill the concepts as we expect. So now what happens when we try and make a function overloaded on these concepts? So we have some calculation that we want to do, and we can do it on a shape or a basic shape. It's fine if we pass it an ellipse, and it says, oh, an ellipse is a basic shape. It's not a shape, so I know which function to call. But then when we call it with a rectangle, the compiler says it's ambiguous because a rectangle is both a basic shape and a shape. So then we scratch our heads and we think, well, I thought that basic shape was more constrained than basic shape. Well, it was in our heads, but it wasn't in a way the compiler could make sense of. Here is what we wrote. And in an attempt to be not repeating ourselves, we put that basic shape t inside our shape concept, hoping that the compiler could see that. In fact, as it told us, it couldn't really see that. And the reason why is this idea of concept subsumption. So this is how the compiler decides whether one concept is somehow more constraining than another. And in order for these functions not to be ambiguous at the point of call, one of these concepts has to subsume the other one, meaning it's strictly more powerful or more constraining. So then you think, what does subsumption actually mean? Well, the standard has some standardese. It kind of works how you'd expect. So you can think about this and sort of go through it. So formally, a constraint subsumes another constraint if and only if the compiler can prove that the first implies the second up to the identity of atomic constraints. And that's kind of an important part. And the compiler converts one constraint to what's called disjunctive normal form and the other to conjunctive normal form, and then basically checks that the set of one clauses subsume the set of the other clauses. So the important part here is up to the identity of atomic constraints, because the compiler, so what we've written here for basic shape, these requires constraints. The compiler can't look inside them. They're atomic. And that's what went wrong here. So basically the subsumption rules, they're formalized, but they kind of work how you'd expect intuitively. So if you've got A and B, that's more powerful than A. Every concept subsumes itself, and A on its own is more powerful than A or B. So it's sort of as you might expect, but here are the gotchas we ran into. So firstly, the only concepts take part in the subsumption. So although you can put a type trait, an underscore V type trait, a context for a bool as a clause in your concept, the compiler can't see through that. It can't take part in subsumption. So only concepts get to subsume other concepts. And that atomic clause says that the compiler basically stops at the level of atomic constraints. So inside that requires all those multiple parts, that whole thing is atomic, the compiler can't see inside. So now it's kind of clear why this didn't subsume originally, and in fact, how to write it so it does. So if we rewrite the shape concept here and put basic shape T on the outside, now the compiler can see that's of the form A and B, right? And that A is basic shape, and of course that subsumes. That means that shape now does subsume basic shape. All right, so we're all good. We write the constraints like this, we write the concepts like this, and then the compiler says, hey, all right, I know how to do that. That's shape subsumes basic shape, and our rectangle call is no longer ambiguous. So that works. Then at some point, we want to do a variadic calculation. One of them takes a bunch of shapes and the other takes a bunch of basic shapes. And at that point, it breaks again. So if these were not variadic, it works and it's fine because we now know that shape subsumes basic shape. But when we make them variadic, somehow the compiler is confused again. So the question is, what happened? Well, what happened was this ended up being something equivalent or equivalent basically to something like this. If I sort of expand out of the terse syntax here and put a manual requires in, the requires becomes sort of like a fold expression, right? And it turns out, annoyingly, that fold expressions are treated as atomic constraints. And because of that, so the one fold expression can basically never subsume another fold expression unless it's identical. So in this case, they're obviously not identical, and the compiler can't look inside them, even though we know that, you know, the shape fold expression subsumes the basic shape fold expression. But the compiler is not allowed to do that, at least not yet. So how do we get around this? Well, the only way I know to work around this is to make the concept itself variadic and to manually put in the requires clauses. So here we've made basic shape and shape variadic very simply by just making the whole thing a fold expression in both cases. We take the, and now we're able to write shape passing through basic shape of T's ... So the compiler is now able to say that shape of t's ... subsumes basic shape of t's ... because it's right there on line 8. The clause is correct. It's kind of textually the same. And then when we write the variadic functions with their sort of manual constraints, manual requires clauses, we can tell the compiler exactly kind of the shape of the requires clause, and it'll be happy. And now it is no longer ambiguous. I don't know. I hope that at some point the compiler will be able to look inside fold expressions, but for right now, it's unable to. And so this is what you have to do, I think, if you want subsumption properly to work with variadic argument functions. So a couple of rules of thumb I came up with. Prefer to use concepts instead of variable templates mostly. When we're building up concepts, remember not to put things inside the requires clause and try and combine them sort of at the top level with ands and ors so the compiler can see them. And also, you know, prefer to use concepts instead of variable templates precisely because only concepts can take part in the subsumption dance. And be careful with variadic functions. So, you know, as with everything, concepts are really cool compared to what came before, but they have some sharp edges. Thank you very much.
Awesome. Thanks, Ben. Very good.
You said
very
that
good.
made the compiler happy, Ben, but it made me sad.
Well, it made me slightly sad too.
You can
Ben
tell.
was
Yeah.
Ben was IMing me about some of these things a few weeks ago, and I'm like, it just looks like a compiler bug to me, Ben. Apparently, it's not a compiler bug.
Yeah.
No, that was not a compiler bug.
So
All
by
right.
to use concepts instead of variadic templates, you mean like a separate concept, basic shape variadic, or maybe a better name, but like all basic shape or something like that, or what?
Sorry, instead of variable templates, i.e. the underscore v things.
Oh, I see. Sorry. Yeah. Okay.
Yeah.
Got it.
And there has been a discussion about fixing that. I don't remember who I was talking to, but I think it was Andrew Sutton. And if it was, like if I remembering that correctly, his response to that was basically, yeah, that's dumb. We should fix that.
Yeah.
Oh.
Okay, so this talk is about an experiment I made in order to verify whether the online development with microcontrollers is possible with C++20. So hopefully you'll enjoy that as much as I did, as it's a huge hobby of mine. So let me just go. So we'll talk about why I've done it, what's the goal, what I used, which libraries I used, a simple project, which will be a switcher in order to verify whether it works or not, and we'll just go through the design, implementation, testing, benchmarking, and simulation, and all of that will be done in 10 minutes, we'll see. We'll have a short demo, hopefully, to showcase the findings I found. So the motivation is often that, maybe not often, but if you like microcontrollers or something like that, you would like to do something with them, but you don't want to buy them upfront. You know, they might be expensive. Here you can see Arduino, which is a quite expensive board for what it actually gives. ATtiny, for example, is compatible with Arduino based on Atmel, much cheaper. Like you can get it below $1. And obviously Raspberry Pi, that's Pi 4, which is pretty awesome, and it's quite cheap as well. So we'll take a look into writing the same project the same way for all of those guys. So the motivation, Arduino IDE, which you can find online, or if you download it, it's not really modern. It's GCC 7, C++11, so no C++20, nothing with Clang or anything like that. So that's a bummer. Simulation online, it's quite difficult if you don't have a microcontroller. There's like Arduino Cloud, but you have to have your own board and other stuff to play with it. So, and you have to pay for it as well. So it's not super easy to do all of that online. And that's where I'm coming with the ideas here. More than C++. Well, if you look into examples, it's C-like kind of thing when you have global variables, and after that, if A and B are not C, whatever else, if, you know, all this code which you see, it's not really C++20, it's not really encouraging to do anything with microcontrollers, I would say, or with any of those code, any of this code. So that's not great, right? In my opinion, at least. So yeah, that's the problem. What's the goal? The goal is to implement a simple project. As I pointed out, it will be a switcher with C++20 for multiple architectures, and we'll use this Arduino Uno, 80 Tiny 85, and Raspberry Pi 4. We'll do it purely online, and that's why this Lightning talk, because you know you don't want to buy, maybe you don't have, or you can't afford, and you just still want to experiment. So we'll do the design, implementation, testing, benchmarking, and the simulation online. We won't deploy it because we won't have devices to deploy it to. But you know, that's the follow-up step which you can do when you have everything ready and you find it interesting or you want to explore it more. So I hope that makes sense. So what tools we'll use? For the design, we'll use PlantUML. It's a great tool to write to design state machines and stuff like, and other diagrams using text, and it will just generate a diagram for you. So it's pretty cool, and it's online as well. For development, we'll use the best tool available, the best website available online, I guess, Compiler Explorer. Everyone knows it. I bet you know it as well. It has GC 9.2 for microcontrollers. It has ARM, Clang trunk, GC trunk, so we can leverage all of them. It allows you to do the cross compilation, so that will be pretty cool because we'll be able to have tests using C++20 and normal Intel compiler and Pi for ARM and AVR for Arduino at the same time. And it also allows you to include the HTTP files, which is obviously not in the standard. There's no proposal, I don't think ever will be, but it allows you to include single header libraries, which is pretty cool, which we'll leverage in that case. So what we'll do for testing, well, not surprise, since I talked about it already, we'll use the UT, it's C++20, single module header, blah, blah, awesome stuff, macro free. That's why we're going to use it, because it's the unit testing framework you want to use. For the implementation, we use state machines because we want to avoid these branches and spaghetti code and all of this crap which we don't want to deal with. And in case of embedded systems, state machines are very common case, like everything is a state there. So we want to do that. And we'll use the SML library, which I'm the author of as well. That's why we're using it. It's because it's cool as well. It's C++14. It's UML 2.5 compliant. If you know UML, it's a single header, so we can include it. Doesn't require anything. No, there's no boost, STL, or anything like that required. So it's pretty cool to experiment if you have microcontrollers and compilers which you can't really leverage because they're so old. And it's obviously fast and it doesn't require exceptions, which is also important for embedded stuff. For the simulation, we'll use Tinkercad. It's an online tool which allows you to simulate quite a few microcontrollers. Doesn't have Raspberry Pi. There's only one Raspberry Pi simulation online by Microsoft, but it's not for C++, so it's dodgy. For Tinkercad, you can use Arduino, 80 Tiny, microbit. There's not that much but you can still play with it. So the project, as I pointed out, would be a switcher. Switcher is just a simple state machine kind of thing, which turn on and off an LED when you switch the button. That's the scenarios for, and as acceptance criteria for it, quite basic. So there's nothing to explain here, I guess. You just have the board and you turn on the switch on the button and you get LED turn on or off. So design will use the implementation with the plant UML. You can read it as source, the transition DSL, you can read it as source state, going to the destination state, event guard, action, that's like UML notation, which you can find in the UML document if you're not familiar with. We don't have time here for it, but the idea is that you start in the off state, and after that, the button is pressed. If it's on, meaning it's the high voltage, you turn on the LED, you go to the on state, and vice versa, you come back. So I hope that makes sense. It's not very, rocket science either way. So implementation will have the component because we want to leverage C++20 and zero overhead abstraction. So we'll use concept here, which will have setup on and off. This concept will be satisfied by LED, which will have the setup, which will set the given pin into output mode, and after that, on and off will verify, will write in that case the high or low voltage for that pin. And for the button, we'll have the setup, which will be an input. On and off will verify the state, whether it's high or low, and whether it's pressed will verify by just digital read. So digital write, read, and pin mode is available in Arduino HPP, and also with wiring Pi with Pi, so can be leveraged the same way. It's quite common implementation. So we have that switcher, as I pointed out, with UML. How we'll do that in SML? SML, it's very similar to what we had before with the UML. So the star means that we start in initial state of event button pressed. When it's on, we turn on the LED, we go to the on state. If we in the on state, we switch it off, we turn off the LED and we go to the off state. So very similar as our design. So that's pretty cool. And that's C++20 and zero overhead abstraction, as we'll see in a second. So the implementation itself, switcher, it takes components. We'll use a nifty trick to go through all of them by leveraging C++20 lambda formula syntax with lambdas, call the setup for them, because we have to call the setup in order to put them in the right mode. And after that, there's just the call operator, which defines the transition table, which we talked already. So that's the switcher. Hope that makes sense. Testing itself will have a main specific for tests. When we will have the fakes, we'll create the switcher and we'll verify whether we start in the off state. And when we process event, which is the interface for the state machine, we'll verify whether it changes the state or not accordingly. So that's nothing special, simple project. The main itself will be a bit different because it's not testing anything, it's putting it into production in a sense. So we'll have the switcher, which will have 3 different types. And we use the abstractions here for button and LED. Depending on the microcontroller, we have to do it differently because we wire it differently. They have different pins, different inputs, different names. So ATtiny will use PB1, PB0. That's the way I wired it. Arduino will use 2 and 11, and Raspberry Pi 4. I actually have 400 and 4 as well, but we'll use 400 here for button 5 and 7. They have the same pins though. And after that, we have the infinite loop, because that's what you do. with the microcontrollers and process the events. Events will be taken from the state machine, so there's no overhead of maintainability. It's just taking them from events, easy, flexible. We call process event all of the events as we go. And the event is a lambda, so it verify the concept on, like for example, button pressed, which we had in the state machine. And if the voltage is high, it will do something, or it's low, depending on our regards. But the basic principle is that we can take the events from the state machine, and if we add them, more of them in the future, we don't have to deal with any of that code. This code will actually never change unless we'll add microcontrollers, and we want to put them in the different with the different pins or something. So let's do the benchmark. What about if we write it in C++03 kind of idea, like all the tutorials? We'll get 44 lines of assembly in for 80 tiny 85. As you see, loop, it's still maintainable, but not in the future if you add more. So that's 44 lines of code. We can do it a bit better without the globals. Just put in the main as well. That's possible if you don't use Arduino, because Arduino requires you to use the setup and the loop in the design. But if you use 80 tiny, you don't have to use Arduino API, whatever, and you can put it in the main. You'll get 32 lines of code. What about if we use our C++20 state machine? We'll get 24 lines of code, which is even better optimized version of what we've just done. So that's pretty cool. It shows that zero overhead abstractions with C++20 might be leveraged, and it's awesome, and it allows us to get the best of both worlds: maintainability, flexibility, and also performance. So just to sum up, if else global C++03 44, C++03 if else 32, C++20 state machine 24. Fantastic. You can check it online as well, experiment with it if you desire, if you don't trust me. So what about the simulation? Quickly go through that. Arduino requires you to do the setup and the loop, but we cannot use libraries there, so C++20 as well, it cannot be used online. So we will use a hack, and in the loop, we'll just put an assembly statement and copy the assembly from the compiler explorer, because why not? We can just do that, and we'll just copy these 24 lines of code generated by compiler explorer and just loop over it. So that will the way it will look for Arduino. Setup loop, assembly, copy the assembly, and that's it. It's the same for 80 tiny. We just copy different instructions because we have to compile it for the different compiler. Because I think it doesn't have call and jump. It uses R jump or R call or something like that. There are differences between different compilers, obviously, different architectures. That's Raspberry Pi. Since we don't have a simulation online, I did experiment and use Pi 400, which is the keyboard, and put a board myself on the bottom so that you can see that the LED will be switched on and off depending on whether you do that, and just to do it in the spirit fashion of experimenting on the weekend. Why not use Kindle to talk to the Pi? Because it's cool. So I use the Kindle variously to talk to the Pi 400 and did the whole project using that. It was pretty fun. So the demo quickly. Design is just plant YML, so don't bother with that. Implementation, you can see we have different includes. As I pointed out, we'll include HTTP, have some fakes, have some different way of calling the configs, but that doesn't really matter. We have all the implementation which I pointed out before and tests. And what is pretty cool here that we have different compilers for different architectures. So that's Arduino for Atmega, that's for the IT Tiny, and that's for the ARM, wherein Pi. Pi requires you to do the wherein Pi setup at front. That's why there's 25 lines of code. And you can also have tests as well, which are running the bottom with the different compiler. So having Compiler Explorer and just explore with all these compilers at the same time is pretty cool. And I find it pretty awesome actually. And just one demo for you. Let's see, AT Tiny online. You can go and actually you can tinker with it if you want. You can edit it. There's a link provided. We will call the simulate here. You can see the code. I copied the code from the Compiler Explorer. I can start the simulation. I switch and it just works as expected. So it's pretty cool. And I guess that's pretty much it. So let's embed all the things. If you are interested in American controllers or something like that and would like to have any guidance of how to start, I'm happy to help. And the libraries which I used, SML and UT, you can find them on GitHub. And yeah, that's it. Thank you very much.
Kris, that's awesome. Yeah, well done. I like it. Yeah, it's fantastic. Kris, do you know, like the AT Tiny, like, you said that those are available for $1. What are you just plugging those into a microcontroller board, or do you have those at all? Are you just using them on the simulation? Like, do you have them physically?
Yeah, I do have them.
Okay.
Yeah, I have, you know, you can, the easiest way is just to have like USB a way to connect to them and just program them via that, or have Arduino board and connect to them as well, because you can connect AT Tiny to Arduino programmer or something like that, or you can just buy a AT Tiny and then buy just a USB way of programming it, and then you can buy AT Tiny for $1 afterward because you will have the programmer.
Okay. All right. Nice. No, that's fascinating. I like how you use the Compiler Explorer also to get the code. That was great.
Yeah, that was the fun part. Copy the assembly, and I was like, oh, because like I tried to, you know, to write any C++ 14 or anything like that, and it just didn't work online. So yeah.
All right. Hi, everyone. Yes, I claim that big O notation is a lie. And if that sounds like clickbait, yeah, it probably is. But you guys can tell me at the end whether it's valid or not. So, okay. We all know what big O is at a group like this. We all know what big O means. Wasn't invented by Knuth, but popularized by him is the way to characterize algorithm performance. And so from a practical point of view, this is how you talk about how your algorithm performs for large N. And so it's usually the primary guiding principle for choosing algorithms when you're worried about performance. And my point is that this can lead you very much astray. The 3 ways I'm going to show you are all things that I hit working at another company back in the 2000s before we had YouTube and you could watch Chandler Carruth explaining all this stuff at a CPP conference. I learned all this the hard way. So the first way that big O can be a lie is that there are special cases, right? So if we consider a sorting algorithm, right? Bubble sort is everyone's favorite bad way to sort things, right? Like, don't do that, right? We all know it's order n squared, whereas standard sort is a good sort algorithm, and that's n log n, right? Right, one of the first big results in theoretical computer science is that n log n is the lower bound on sorting, right? So standard sort does that, great. But here's the thing. What if the range is already sorted? And you might think that that's kind of a silly thing. If it's already sorted, why are you sorting it? But You don't always know. Maybe it was processed by some other thing before it got to you, and it might be sorted. Here's the thing. Depending on how you write your bubble sort, if your range of stuff is already sorted, bubble sort runs in order n, right? Because it just goes through it once and says, oh, look, it's sorted, I'm done, right? So you get a big improvement in bubble sort in this particular case, whereas standard sort is still, at this point, comparatively slow. Or what if you have one element out of place, right? You've taken the last element and rotated the whole thing so that it's first, right? Again, depending on how you write your bubble sort, this is still order n, whereas standard sort is still going to be an n log n operation. So the point is that many algorithms have special best or worst case situations, but it's order n or n squared or whatever it is usually just the average case or the typical case. You may be very surprised to find out that you're in one of these special cases. So when you select your algorithm, read the fine print. Now, the second example, the second way that things can go awry is that you have to define what big means. And we didn't plan this, but this is almost exactly the same kind of thing that Jacob was talking about. We're going to make all pairs of something. But this is the first stage in a multi-stage thing. We're solving a problem that is fundamentally combinatorial, right? The thing you have to do is basically n factorial. And so you go to great lengths to haul that all the way down to something as good as like n to the sixth or something. And this is kind of the first stage in that. So what you've got is two sets of things. Each set is, so you got set A, set B. They each have n objects, and you want to find all pairs according to some multiple criteria, which could be very complex. So this could be things like you want all pairs that are, that are physically close in space, or they have the same color, or they have similar signal to noise ratios or something. And some of these could be very simple. Some are very computationally expensive. And the criteria you're going to apply and the order that you apply them in is either specified in a configuration fail, or sometimes you will adapt at runtime and change them. So the implementation that we had at the time was to use standard sets. And we all now, you grit your teeth, oh my God, it's going to be slow. Yeah, it was slow, but this honestly worked for like a decade or something, right? So the idea is you take set B and you sort it in multiple ways, one for each criteria. So you end up with multiple sets, one for each criteria. And so for a given element A, you can sort of look up in one of those sorted sets of B, like where it would be, and then, or you might do like a lower bound and an upper bound to find all the ones that have the same value. Or if you want nearest neighbors, you would find where A would be in B, and then you traverse, you iterate forward and backwards in that sorted set to find the ones that are in some sense close. So I mean, this is a very complicated thing, right? This is kind of the high level view. And so when you get to the end of this, you get something that's very heavy in standard set operations, and it's something like n plus m times log n. Now, m is something like the number of matches you get from each criterion. And what you want is for m to be small, right? That means that your criterion filters out a lot of things you don't want. Or put it the other way, the value of m that you actually get from one of these tells you how hard your problem is, how hard it is to eliminate possibilities. Now, for the real problem that we were solving at the time, n equals 50 was considered hard. 300 was typically impossible, except unless the problem was very simple. Like you could do 300 if m is always coming out, 1 or 2 or something. I tried to feed it a problem size of a couple of thousand once, and we couldn't even set the problem up before we ran the Beowulf cluster out of memory, right? So it was a challenging situation. But after a while, we finally did, first of all, figure out that standard set is slow, but we came up with a very clever way of reformulating this, which I'm still proud of. I don't work at the company anymore. It's their intellectual property, so I won't describe it in detail, and I don't remember it anyway. But the idea is to represent everything in terms of boost dynamic bit sets. So instead of having like a standard set sorted in accordance to one of these criteria, what you would do is arrange for some number of dynamic bit sets, and then an on or off bit represents one object in B, and you arrange for your dynamic bit sets to have bits on or off that represent say, closely grouped chunks of B or something like that. So you would bin objects from set B into groups. You arrange for a dynamic bit set of each group. So for an element in A, you find the set of dynamic bit sets that match the criteria you want. You bitwise OR those together, and then across all your criteria, you bitwise AND them together to do a sort intersect. This was a detailed, complicated bit of business, but it pretty much gave you exactly the same results as the other thing and was way faster, like way faster. As in, what before would chew up 40% of your runtime is now 5% of your runtime. And the things you were worried about profiling, or that your profiler was telling you should optimize, simply disappear. The compiler optimizes them out, they're gone, right? This was very successful, but then things got interesting because the mathematicians at the company looked at this and they called, well, politely, they called horsebucky, right? They said, wait a minute, I don't buy it. There's something else going on. There's something wrong here. I don't buy this. And the reason why is that the dynamic bit set, doing a bitwise AND or a bitwise OR to put all these together, that's order n. It's order n over 64 because dynamic bit set stores all of your bits in, unsigned longs, right? But still, you've got, maybe n divided by 64 of these to do as you iterate through and bitwise operate on them. So it's still order n. And for various complicated reasons, you end up having something like n of these dynamic bit sets. So the result ought to be something more or less kind of like an order n squared thing, as compared to an n log n, which is what we had before with the standard set approach. So the point being is that me and my coworker were claiming that an order n squared operation is way faster than an n log n operation. The mathematician said, I don't buy it. So we spent a bunch of time, we ran a bunch of simulations and came up with a bunch of scenarios, and we found that the point at which n squared was as slow, that the dynamic bit set n squared variant was as slow as the standard set approach, which is n log n, was something like, I think it was about 700,000. It had enough digits in it that you had to mentally count over and put the commas in, right? In a problem where 300 is considered large, okay? So we said, wait a minute, what's up? Why is this n squared operation so much faster? And the answer, of course, this is what you've all been waiting for, is cache hits. These are numbers I stole from Chandler Carruth's talk from 4 or 5 years back at CPPCon. The point is that an L1 cache reference is something like half a nanosecond, whereas going out to main memory is, say, 100 nanoseconds. So it's 2 orders of magnitude. Standard set is node-based. We all know this. So every time you do anything to it, you're taking a trip out to main memory. So its order, let's put the constant in, 100 n log n. Technically, there might be 100 inside the log n, but never mind, this is good enough. Whereas dynamic bit set is a contiguous array of 64-bit integers. So every time you do anything to it, it's an L1 cache reference, so it's 0.5 nanoseconds, and you do n over 64 of them. So there's a 0.5 over 64 out in front of that. So if you actually plot that, you'll find that your n squared operation is faster than n log n for everything less than, say, what, 150,000? Okay, and here's the point, right? Big O notation tells you about what the asymptotic behavior of your algorithm is for large n. But how large is large? In this particular case, large is bigger than 150,000, and we're way the heck down here, where 200 or 300 is something we can't really handle. So the point is that in this case, big O is meaningless because that only means something if you're talking about an asymptotic behavior. So the point being is that what big really means is determined by all those constants that everyone usually wants to ignore, okay? And if your n isn't actually big, then which algorithm is going to be faster can be very surprising because your big O notation is basically lying to you about what it's really going to do. Big O is meaningless unless n is big, and you might not know what big means. You might have to go measure. All right. Now, the third thing where big O notation can trip you up is that there's an assumption that small means easy, right? We only worry about big N. We only worry about the performance of our algorithms for big data sets because of the assumption that if N is small, it's going to run fast anyway and you don't care, right? If you're only sorting 20 things, who cares whether it's fast or slow? On a modern computer, you won't notice, okay? So consider a problem statement, which is a follow-on to that previous thing, right? All those pairs that we were trying to make the number of pairs as small as possible, those end up feeding into hypotheses. So a hypothesis is a set of observations. Observations in real life may or may not arrive in time order because you've got multiple sensors and there's like network delay or something. But the operations you're going to carry out on these hypotheses require time-ordered data. So you have to keep these hypotheses sorted as new stuff comes in, right? So how are you going to do that? How are you going to keep your data sorted as these things come in and you keep adding them? Well, our original implementation was, again, standard set, because back in the early 2000s, that's what you used for these. And okay, fine, we learned that standard set is slow, and so we went to, say, a standard vector plus a standard sort, because that's what you do to sort stuff. But of course, what we found is that, okay, you might think that for n equals 20, and that was typically the biggest size that a hypothesis would be. Look, it doesn't matter what you do, it's fast, and this is actually true. It doesn't matter what you do until you've got 200 million of these things to handle. And 200 million hypotheses was not a difficult problem, okay? I mean, or rather to say it's difficult, but this was typical, right? And if you've got that many 20 element things to sort, the behavior for, or your performance for n equals 20 becomes really important. So the point is that while standard set insert is, you've already got a standard set and you're going to add one, that's ordered log n, right? That's going to be fast. But consider that a standard vector you push back and you call a standard sort, well, it's order 1 amortized for the pushback, you know, and then it's n log n for the sort or something. But of course, it's in a standard vector, so it's going to be much faster. We found that out. But remember, we talked about earlier, I mean, bubble sort is usually slow, but bubble sort can be order n if it's already sorted except for one guy that's out of order and he's always on the end and you bubble sort the right way. So you go to a standard vector with a pushback and a bubble sort. And now when you're doing order 1 plus order n for a billion hypotheses, this makes a huge difference in runtime. Although even if it was this, it's actually a fact that bubble sort is faster for small things than standard sort is. That n squared, yeah, is totally swamped by the fact that the algorithm is so fast and so simple, and the compiler can optimize it, right? And everything's local. So the point is, and of course, what you really do is you just start doing a linear search from the back to find out where your new guy goes, and you put him in because he's almost always going to be near one end of this thing. So you do this and you optimize for a small case, which ordinarily you wouldn't worry about. And again, we got huge speed ups, like factor of 2 or something. All right. And so when you're doing 100 million or a billion of these, the n in your algorithm isn't the important thing. It's how many times you have to run it. And in that case, standard wisdom for what, you know, what the big O behavior of your algorithm is, again, totally irrelevant. All right. Because the fast ones are the ones that big O notation would say you shouldn't even look at. So the point is that big O notation is a lie. Now, it's not a malicious lie. It's a lie we tell to children, right? Because the universe is complicated. And it's still a good first guess. I mean, you don't know which algorithm to use the one that looks fastest, right? Just keep in mind that this can be deeply misleading because you've got special cases. The constants out in front matter, AKA really what that really comes down to is cache locality. Cache locality typically swamps all other considerations. And even behavior on small cases matters when you've got a large number of small things to do. So I claim that big O notation is a lie, sometimes. Thank you.
Nice. Good job, Dave. Thanks.
You guys can tell me whether that's too clickbaity as a title.
It's kind of like a big O notation as Santa Claus.
Oh, that is, yep. I will absolutely go for that.
Especially in December, you know, that fits.
Yeah, I'm sorry I didn't think of it. Whoops, hang on. I am now. Let's see if I can kill that without. There we go.
Yeah, you
That's
did.
awesome.
You're good.
Good. All right.
That's awesome. Thanks, Dave. That's great.
All you youngins with your newfangled online meetings.
All right, Jason, you are up.
All right.
Sorry, can I just mention on that? Great talk, Dave.
Thank you.
I feel like one of the other poster children for that is, lower bound versus find, where find usually handily beats lower bound because of the branch prediction.
Ooh. I hadn't come
Until you
across
have
that.
large, of course, how big is big?
Right. Yeah. Oh, I hadn't thought of that. Oh, that's a good
Because
one.
find is perfect for the branch predictor. As soon as the branch predictor fails, you're done. Whereas lower bound basically is random for the branch predictor.
Yeah, and in small sets, linear search almost always beats binary search. I
Yes.
think similar reasons. Yeah.
Right.
Yeah.
All of that also flies back to Chris's, like if it really matters, then actually do it and measure it, right?
Yeah.
Run some tests and
Right.
measure it, because
I mean,
all this
yeah.
stuff is too complicated
Right.
to be able to look at it and predict reliably. Yeah.
Mhm.
Right.
Dave,
and
did you see Paul's comment, the big O tooth fairy?
the big O tooth fairy? See, if I'd asked you guys about it before, then it wouldn't have been a joke. But that's awesome. It's either the tooth fairy or Santa Claus. I like it.
Yeah.
The big thing that stuck with me about this, because like I said, this was a while back, was the mathematicians, and these were brilliant mathematicians, coming to us and saying, you can't possibly think this is faster because it's n squared. And we're like, but dude, the profiler don't lie. And the reason is because n is minuscule. But we all thought that n was big, right? So yeah.
Awesome.
All right, anyway.
Good stuff. Thanks, Dave.
My
All
pleasure.
right, Jason, you're up.
Right. So my lightning talk, I assume everyone can see this. Let me know if you see any problems here. My lightning talk was supposed to be C++ 14 Lambda coroutines, which is a little thing that I played with and I shared on Twitter a few months ago, and I thought it would be fun to talk about. But then I decided last night to switch it to Who Wants Reflection, because this is something that I've been playing with lately. And I actually delivered something like this to a client recently. And so okay. Everyone wants reflection, right? C++ 23, hopefully we get reflection. And how nice would it be that if we had some struct that we could just say, hey, give me the members to it. And if I get the 0th member, then I get its value as 42. If I get the 0th member's name, then I see that this is X, right? Everyone wants something like this. With reflection, so much is possible, most notably easy to implement serialization and deserialization, right? And just for the record, this lightning talk is going to go super fast. It might be like 5 minutes by the time I'm done here. It depends on how much time we spend in a minute here. So once we have reflection, we could do something, like crazy, like say, let's visit all of the members of some object S here. And for each member, print out its name and value. That would be awesome, right? And then it's really easy to start to see how implementing something like to JSON and from JSON with easy to use serialization would be easy in here, because all we have to do is visit each of the members, walk over them, and add them to this JSON object, right? It's easy. We just call to JSON here. C++ has no way to do this, right? If C++ had a way to do this, we would all already know about it. It doesn't right now. Are you willing to give your compiler just a little bit of help? No, Jacob says no. Just a little bit of help? Okay. Is this too much to ask, that I have a context per static array with the names of my values, of my members? That's all I'm asking you to provide. Is that too much? For some of you, it's too much. Okay. That's all we have to provide. And now all of these things are actually relatively easy to implement. Wow, this is going to be a lightning talk. This is what I get for not, yes, I want to allow that, for not walking through this first, but that's okay. Oh my goodness. New browser. Yes, I consent to all of the things. Okay, so I've got my example test case down here. I've got my struct S, and I've got my static constexpr array of member names. That's all I have to do. I'm using C++17's class template argument deduction CTAD right here to figure out that this is 2 values of type const char pointer. And then I actually can write a function called visit members, and I can walk through each of the members, and I can print out, this is your name and this is your value. Bam. It's all I had to do was give it the array of names. Now the question is, how much do we want to walk through the implementation? One did it very badly 3 years ago.
Yeah, I'm totally interested. Maybe nobody else is, but
yes, I want to see all this
bitten by this
implementation.
so badly, I can't even tell you.
I have no idea how you did this.
It's super simple. It's actually super simple. You can see it's 91 lines of code, right? That's all that it is. Okay, so I've got my visit members function. It takes the visitor and it takes the object, and I forward that to something else where I need the index sequence. The index sequence is based off of the size of the set of members that was passed into me. That's fine. This is my visit members implementation. And I do a variadic fold expression, C++17 fold expression here over the comma operator, expand it here. And I'm just saying get each thing and pass that to the function individually. No big deal. But how do I actually get the set of members? That's the fun part. And I've implemented this now at least 3 times. So I'm really refining the way that I'm doing this at the moment. So I've got this get members function here. I pass in an object to it. Is the size of the font readable? Should I make it bigger? Okay, it's fine. I get 1 thumbs up. All right, so I want to say, how do I get the number of members? And I've got 2 different options here. One is if I actually just provide a num members. So I want to just take a quick diversion here. If I comment this out and I take this, oops. If I do it like this instead, then I can still do this reflection, but I don't know the name of the values
I
anymore.
don't think that should be a standard array.
Yes, thank you. You could see that I was trying to think, why is it not compiling right now? There we go. All right, so I can get the members with their values, but I don't know their names because I didn't provide their names. Okay. So I've got this little helper lambda that I'm immediately invoking that says get the number of members if, because I'm using this if constexpr trick that I learned from Kris, and I did a recent C++ Weekly episode about. This trick is unbelievably useful here. So this is C++20. I'm saying if constexpr, and then I'm using a requires expression, which returns a Boolean at compile time. If this thing has a num members, return the num members. Otherwise, return the size of the array that the member names is. And then for my names, I'm saying if it has a member names, then return the member names. Otherwise, return an empty string view array. Okay. So now then in here, I calculate the num members. That's based off of the size up here. And I just do a bunch of if constexpr conditions. If constexpr num members equals 0, then return an empty tuple. If the number of members equals 1, this is where it gets a little annoying because there is no way to do this in a variadic sense in C++ today. So we have to do one of these if constexpr clauses for each possible number of members, but copying and pasting up to 10, 20 is not that difficult. So for each one of these, I am doing a C++ 17, what's that called?
Structure binding.
Structured binding, thank you, Ben. I'm doing a structured binding, and I am forwarding the object. So whatever was passed into me, and I'm doing this forwarding reference here, just to continue that type forward. And then I do forward members as tuple. And this is inspired by the forward as tuple C++11 utility function. And I pass in the names and all of the parameters. I'm forwarding each of the parameters in here. The forward members as tuple is not that complicated either. I've just got a simple inline lambda here that lets me get the name of each member that was passed to me. And if the array of names passed to me is empty, then I'm just going to return an empty string view for each of them. Otherwise, I'll return the name that exists there. And then I am creating a tuple and returning it. And I'm using the same implementation that forward as tuple would give you. So I have this little member wrapper here with a string view for the name and the value. And I am using something that should work on every compiler because it's required as of C++11. But if you've been following any of my tweet rants recently, you know that that GCC gets this wrong in a few cases. So I'm just doing a, so if something is inside of braced initialization here, it is required to be strictly evaluated left to right. So I am doing just an index plus plus. So it's going to get the name for the 0th, 1, whatever, all the way up. And I'm doing a forward of the arg passed into me, and that's it. So the only tricky bit here is that I have to do these crap, Ben.
Structured binding.
Structured bindings, thank you.
Ironically, I never remember what it's called. I always want to call it destructuring bind, which is from Lisp, but
yeah,
structured
destructuring in other languages, structured binding in C++17. So I'm doing these structured bindings here. That's the only tricky bit, and then a little bit of template magic to unfold it. And that's all you need then. You just have to be willing to give your compiler a tiny bit of help, the number of members or the names of the members, and it'll sort it out for you. Is that acceptable? All right, if you got C++20, it's 91 lines of code. I'll share this in the thing in a moment here. Oh, and for the question of whether it's compile time or runtime, this is all const expert, can be done at compile time. It is doing the work at compile time. If we look at the actual disassembly, it is getting the value 42 here and getting whatever, it's getting the values that it needs for formatting these arguments and the names, and then just passing them straight off to print. Like the compiler figured all of this out at compile time. It's really straightforward. But it's const expert. You can do it at compile time, you can do it at runtime, whatever. That's what I got.
Nice. Well done. Thank you.
That is absolutely awesome. And I wish I had had it 3 years ago.
Oh, wrong link. How'd that
We're
happen?
on a C++ 98 compiler, but yeah.
And you know, if you're copying and pasting more than 20 arguments anyway, then maybe your class is too big, or
Your class is too big anyhow.
This whole time I was thinking about, in this legacy code base that I'm in, I have a class that has 93 members. I was like, oh, I don't want to do this.
No, you don't use it here. But that copy and paste, right? That has to happen exactly once for your entire code base.
Yeah.
And that's the only downfall here. And I know that there's some discussion about being able to do variadic expansion inside of structured bindings. We just don't have it yet. And that would simplify the rest of this. Oh, and I just want to jump to this here, that I do have, I have actually implemented this in my C++ weekly game project live stream stuff that I did a couple of months ago, where I actually did use this technique for from JSON and to JSON, but I ended up making it a little bit too specific. Like I said, this is the third time implementing it. So now I know that I could actually take the code that I just wrote and just jam it into here, and it would just be like magic.
Nice.
it requires that all of your members are public too, right?
No, not in C++20.
You can't structure bind private members.
In C++20, you can structure bind visible members.
Right. Okay,
So
you have friends sprinkled around.
yes, or if you only want to serialize and deserialize the public members, then from the public visibility of this, then you should work. I've done another implementation of it that used CTRP and then CRTP, excuse me. And so that in that case, then you could have the private members as well if you made your base class a friend or whatever. And then you could make it magically work that way with CRTP. Also, it only takes a little tweak to make it CRTP version.
I have one of the APIs I work on has a struct with 100 members.
Yeah, you know what? You all are working on things that just shouldn't exist. I take no.
This is
You mean we're working on real code? It exists.
Yeah, that shouldn't
That's
kill
life.
it.
It shouldn't,
now.
but that's how it is
Kill
in real life.
Oh, awesome. Good job, Jason. Thank you very much. Let's see, Tim.
This is a lie. But this is my talk for, let's see. Yeah, this is my talk for the North Denver Metro C++ users group. My daughter says it sounds like we're a bunch of users. And so, yeah, hi, my name is Tim and I'm a user. I've been using for about 25 years and I use at work. I work for a company called Peerless Network. And when you think about it, it's kind of an unfortunate name for a network company. But part of Peerless's business is wholesale telephony. So we connect calls from customers who are our telecom carriers, using other carriers as vendors. And calls originate from a calling party, pass through one or more switches, one or two of which may be ours, to reach the called party. Each switch generates a call detail record. This is the infamous metadata. What does it look like? Well, just a bunch of name value pairs, like calling and called number. What do we do with this metadata? Well, if you're the CIA, apparently you kill people with metadata, but we do not kill people with. Part of my job is to take the call records and add even more fields that are relevant to the business based on complicated business rules and reference data, and send them downstream to systems like OLAP and billing systems. As an example, suppose we want to add the name of the caller's switch. We have to refer to some external reference data called the LERG, which maps the first few digits of a telephone number to a location and switch. So how do you identify a switch? Yep, we'll use a silly name or a code where silly is spelled CLLI, such as this Denver CO26DS1. SLLI stands for Common Language Location Identifier. And silly names are registered with a company called iConnective. So iConnective is effectively the ministry of silly names. They have the market cornered on silly. So if the calling number, say, starts with 303-555, the LERG tells us that this call is from a switch in Denver, say. 202-555 might map to a switch in Newark. And then sometimes, the call is coming from inside the house. This is maybe more relevant for today. So you could say my work is enriching, but really, is it fulfilling? The fulfilling part is, comes with the software development and making sure we can maintain throughput and reliability. We don't want the CDRs backing up and spilling all over the floor. So to do so, there's some self-imposed constraints. No per record disk IO, no network service dependencies when we're doing this. And how do we get away with that? Well, as long as the data changes slowly, like every 10 minutes or daily or monthly, we can work with snapshots of it. And as long as it fits into memory, we're good. Until the day we encounter something that doesn't fit those assumptions. Like what I told you about looking up a switch from a telephone number is a lie. I'm still getting over the big O, sorry. To find the switch, you actually have to look up another telephone number called an LRN from a different database called the NPAC. The LRN is kind of like a telephone number for a switch. And if you find the LRN for that number, then you have to use that to look up the switch instead. Otherwise, you use the original number. Yes, it's kind of an example of the fundamental theorem of software engineering. or you can solve any problem by introducing another level of indirection. And I love that Wikipedia describes it as originated by Andrew Koenig to describe a remark by Butler Lamson, attributed to David Wheeler. Our problem is how to fit the NPAC into memory. The 8 gig text input data that we get is 420 million lines of 2 10-digit numbers. So my numbers are bigger than yours, Dave. Wow. The number we are looking up and its LRN are in that file. We'll treat the A gig as an upper bound and round estimates to say 400 million rows, because that's close enough. And so how do you fit that into memory? Well, you can find more memory, find a space efficient representation, and maybe we'll target 1 gig just because I feel bad about it. Asking for more just to enrich this one thing. But cool, this is like the introduction to John Bentley's Programming Pearls, where he has to sort 10 million 7-digit toll-free numbers in 1 megabyte of memory. And so like I'm living the dream. This is like fun stuff. Spoiler, he uses a bitmap as a sorted container, but you knew that already from yeah, and some less important goals. We're going to just focus on this one particular problem and not worry necessarily about it running on all platforms. And if we find something that's good enough, we'll just move on. We won't optimize it. So we could reach for a sorted array of telephone number LRN pairs, which has the advantage that there's no overhead in storing the data. The downside is that it's huge and would encounter lots of cache misses. But then again, that's getting a little greedy because first we have to get it into memory to worry about that. One obvious step is to store these values as binary integers instead of strings. Of course, it would be the case that a 10-digit telephone number has a 33-bit range, but we can at least take care of the keys by splitting them into 2 tables, one for the low half of the range and the other for the high half. And then we just have to transform them on the way in. We could possibly do something similar with the LRN, split each table into 2 more for a low and a high LRN range. And that would require 2 lookups. But instead, let's just count the number of distinct LRNs. Remember, an LRN is like a telephone number for a switch. And so how many switches could there possibly be? And it looks like there are about 38,000 distinct LRNs, which we can conveniently fit into 2 bytes, giving us a size of 2.4 gig. That's an improvement. Looking at this some more, you'll notice that we took the most significant bit from the 10-digit number and made it disappear by just splitting the table. Can we do that with subsequent digits? And of course, some of you already recognize that as a tree. So how to recognize different types of trees from quite a long way away. Number 1, the large, the large. Number 3, the prefix tree. A little closer. I don't know if hopefully you can see that. The idea, you all know what a prefix tree is. The idea is that the children of the tree share the same key prefix as their parent. So you don't have to explicitly store every digit of the prefix for each value, only the shared prefixes. And at each level, you dispatch to a deeper node based on the next digit by following a pointer until at the end, you store a value instead of storing a pointer. In this case, our 2-byte LRNs. There's a node for every unique prefix. So if we can count the prefixes, we can count all the nodes. Just a hint, if you sort the keys ahead of time, then you can traverse the tree kind of in order and only need to keep a track of the current single node at each level. We can cut off the last digit of each number, eliminate the remaining consecutive duplicates and count them. And you can use the output of that stage to count the nodes at the next level. And as expected, the number of nodes grows exponentially at each level. So you really only have to consider the size of the last 2 levels, say. But, and let's see. Anyway, just assigning some costs to per node costs at the different levels based on what I expected they'd have to index. I ended up with 2.3 gig for that. So we really didn't gain much by going to a prefix tree, unfortunately. Let's just run gzip just for kicks to make us feel a little bit better, and that gets down to 1.3, but I can't really use that. Number 4, so let's try something else. The Patricia tree, it's a prefix tree, but merges nodes along a single path. So any node that has only a single child, you can combine that 2 nodes like that with the next. The short answer here is that I measured it, and our 10-digit nodes don't often have that single descendant. Maybe a binary 1-bit prefix tree might work better for that, but no, you have more levels, and it's kind of convenient with telephone numbers to stick with decimal digits. Number 5, I ran across the Judy array, which at first glance sounded great, but I had no hope of implementing it, especially in a persistent store, which was the plan. It's a 256-bit radix prefix tree, and really they optimized the hell out of it to be friendly for CPU caches. It's just really extremely complicated. The diagram from the Judy shop manual sums it up pretty well for me, where you can see the theoretical limit for a given problem in time and space along some curve, and then the actual limit for the talents of this programmer, which is me, which is way, way far away. So I didn't really have much hope with that, although it's tempting because this seems impressive. If you can use it, then you can beat the theoretical limit through the caching tunnel where Judy is operating. They're just teasing me. But at least, we can set a lower bound for what we could hope for if we stored just only the 2-byte values that would be required for any of those tree varieties. If we didn't have to worry about keys, we could reach 800 megabytes. Cool. But let's think about those LRNs again. How many unique LRNs can even exist at the lowest levels of the trees in any particular node? Like at level 9, there's only 10 choices. Going up to level 7, there are 1,000. So let's look for each level. Running down the slide on the left, we count the number of nodes having an LRN count of 1, 2, 4, 8, 16, and so on, all up to 38,000. And the ranges are chosen here to reflect the number of bits that we would need to represent each LRN at that cardinality. So at level 7, you would need a maximum of 8 bits per LRN per node. Sorry, and most nodes just require 5 bits at that level. Each node might have a different set of LRNs, but within the node, we only need at most 5 bits for itself and its children. So here's the approach. We're going to pick an appropriate level. I picked 7 digits, prefixing of the 1,000 block. And at each node, keep track of the unique 16-bit LRN IDs that we used before, used under that node. Store those in an array that's sized per node. The indexes into that array become a new block LRN ID. So we'll determine the minimum number of bits we need to represent those IDs and store another per node array of those 1,000 packed n-bit integers. This is kind of what it looks like. Sorry, the names are probably not too meaningful to you. Here's the structure looks like this. It's a header followed by 2 arrays that are custom sized per node, a packed array of n-bit integers, followed by an array of the 16-bit LRN IDs stored in order of their smaller n-bit indexes. And you just have to, there's an offset that jumps you so you can find, when you're seeking there, you can find the second array once you pointed to this structure. This is what it looks like. Instead of a bunch of levels at each digit, we just have 2 levels. Just because the ends in this NPA and XX are restricted to, they can't be 0 or 1. So I couldn't resist, just like cut them off. Why represent them? Although it really doesn't matter. There are only 1,000 of these. If you have an extra 1,000 32-bit words, it's not significant. There's another reason to actually break it, and that the thousands digit, the NXXK, just because I had to stash another number in there. So that's another reason. But it also made sense. And so, dare I say, it's portable. 659 megabytes is CD-ROM sized. I won't feel too guilty about blocking that into memory. Okay, so I have to mention the word succinct because it's in the title of my talk. I ran across this library, but didn't end up using it just because I really did need control of the layout, because this is like a persistent data structure and I can't really have things changing. But succinct data structures can represent an object such as a bit vector or a tree in space close to the information theoretic lower bound of the object while supporting operations of the original object efficiently. So that's a neat term that I learned while I came across, and there are libraries of succinct data structures, which would all be really nice to use, especially if you're just putting them into memory and not storing them on disk. I ended up rolling my own integer packing class. It is kind of a view on some storage that's blocked out and allows you to store just integers of arbitrary bit lengths. Almost certainly has a bug in there somewhere, but the nice thing about this constant database that I build is you have every positive test case available to test before you actually deploy the thing. So you can run every at least positive lookup. This is deployed by creating a binary image in a file, and then processes just share the file by mapping it read-only. We'll just rely on paging for I/O, set some pointers into it, and use the data in situ. C++ is great for this. And then if you really don't want the I/O, you can have a root-on process that just locks that file in memory, keeps it around. So in conclusion, I have learned that if you want succinct, you really do need to create your last slides first. So thank you.
Thanks, Tim. That's I like the anecdotes. It's awesome. Awesome. Okay, while we're switching up here, does anybody have any questions for Tim? I guess one of the questions I've got, Tim, is like, how old is this database, or how old's the structure that you have to maintain?
This structure is probably about 3 or 4 years old.
Okay. All right.
It hasn't required any changes in the format of it, which would be not too big of a trick to deploy, but it works.
Nice.
Good running.
Nice. Kaz, you're up.
Yes. All right. So I'm going to go over kind of a brief history of coroutines as I've understood them. And a lot of this is based in the microcontroller world, so hopefully it'll be familiar.
You can feel free to turn on your video if you would like to.
My laptop is closed and I'm using my cool monitor. I wish I could turn on my video.
Okay.
So the problem is we write serial programs for serial processors. In my current microcontroller project, I want to indicate that everything is fine via an LED. And here I've written a small, simple to understand program to map that everything is fine to an LED. And it's short, it's a seed. This while loop here is pretty cool. I've exported this to a library, and here I'm going to use my main loop, my main eternal servitude loop. I'm going to indicate that everything is fine, and I'm also going to adjust the chlorine distribution in the pool. Veterans will recognize that this is fine, and it's not. Main control never returns to the loop. We're never able to call adjust chlorine levels because this subroutine has hogged the processor and will not let it go. This is where coroutines come into play. A coroutine is a subroutine that we want to resume execution where we left off. But translating subroutines into coroutines, or rather changing something into a coroutine when you only have a subroutine structure in your language is a bit difficult. We need to switch up this function. I'm going to identify a local state of the function, control flow, and side effect. The countdown is my only local state within the function that I need to be persistent. My problematic control flow is this while loop and this if statement. Well, not the if statement. The if statement's fine. I've also highlighted side effect here because I wanted to highlight everything. We need to rearrange this, get rid of the while loop. Assume that we're going to be called within a while loop for this function. So I'm going to move it outside of my function, unify it with the one eternal loop, which is to say, while one, do everything. I've used true to indicate other conditions for when I want my program to continue. And I've also cut out a little section here of my while loop to execute and indicate that everything is fine. Unfortunately, I also need to extend local state scope beyond my function. So move it up here, change my function's interface to have an external mutable, move the screen over a little bit. And basically, I'm just going to fix syntax really quick to so that this makes sense and is compilable. Voila, I've created a function that is cooperative, a coroutine before coroutines existed. I've called it within my main loop, and now all my other tasks can be written in parallel with this main loop to get concurrent execution, assuming everybody else also plays nicely. I hate doing this so much. I'm not sure I can emphasize this. I've done it for like 5 years with microcontrollers. In my first 5 years of my career, so please forgive me. There are better ways to do this now. But there's a lot of problems with writing code like this when the language does not supply a way to write coroutines. If you're using subroutines to emulate coroutines, things just become hard to debug, and we're kind of fighting the language as we go along. For reference, I have this small blinky LED program, but I've seen a couple of TCP stacks written for microcontrollers, and one was, no joke, a 9,000 line function with go-tos and labels. It was horrendous. I feel like it should be mentioned here. This is because part of the issue here might be because I'm trying to solve a functional problem with a procedure. If I was using a reactive framework and a pure functional mapping, this would not be an issue. I could just invoke this routine in a timer interrupt event. But I'm going to pretend it's a procedural problem because the machines I work with have procedures and states. So the obvious solution, which I expect everybody else here to use, is standard thread. It's cool. Not applicable for my stuff. I'm working on a microcontroller with like 40 kilobytes of SRAM, and I'm too stubborn to install an operating system. So not quite yet. The third solution is Boost Coroutine. Boost Coroutine secretly uses Unix context, and Unix context were going to be a thing, but most everybody decided, hey, thread's better and we should be using thread. Now, I've written my same function here with 2 modifications for Boost Coroutine. And I guess I should try to establish Boost Coroutine creates an object that tries to handle while being a coroutine. The first change is an argument pointer on the function stack pointing to off the function stack. And I feel like that should be mentioned here. Stacks can be segmented. So where the caller is from, they may not share the same stack as this function that I've written here for. The other change is this sync call right here, which basically says, hey, now's a good time where I can pause and be interrupted and let other people run. So Unix context, I need to talk about a little bit. A Unix context is basically a snapshot of the processor state within a function. Basically, we're saving the caller's stack pointer, a link register back to the caller, and the caller's variable registers. And we're saving that to a data structure. Here in sync, we're doing the same thing for this function. And then we're replacing all the processor's registers with the previous caller's registers. So it's a very effective go-to effectively, a stack safe go-to instruction. It's cool, I like it. Swap context is faster than a thread switch, but it's also not optimal. The context saving routines are very safe, which means they save all variables, possible variable registers. Like on the Cortex M4 I'm working on, there's like 64 bytes of floating point registers, which I don't need to save or restore because I'm not using them in my particular context. In fact, I might be able to get away with like 16 bytes of reading and writing. But it's cool and it works. I've put a rabbit here to indicate, hey, I haven't gone too deep into this. That's significant because solution 4 gets 2 rabbits. I was going to write about how I wrote my own context routines for restoring and so on, and a fiber scheduler. And then I learned that C++20 actually has coroutines coming out in GCC 10. So I've rewritten my code here. It does compile. And the important part down here is this co-await, new keyword for C++10. The big issue here is I have no idea if this works or not. And I promised myself last night that I would figure out how to write this by reading over the technical spec. Still hasn't happened. But I didn't know that when I committed to this topic 4 days ago. Anyway, I done goofed and I thought I understood where C++20 was going to go with coroutines, and I don't. My bad. Let's see if I can. Thank you.
I like the honesty. It's good.
Okay, so I'm going to be presenting quantum interpretations of the C++ object model. So first, just real quick, I just want to go through some of the basics, just to kind of make sure everyone's on the same page. I expect that all of you pretty much know all of this. So first we have a tree BQP. It's a subset of the third level of polynomial hierarchy, PH. We have Raz's technique, which shows that the permanent and determinant of a matrix requires superpolynomial size and multilinear formulas. And here's a sample Shor state. And then just a quick refresher, I don't think I need to explain this. This stuff is all pretty obvious. So I know what you're all thinking right now, obviously. Don't worry, that's actually not what my presentation's about. That's just random quantum mechanics stuff I pulled from a paper. Here's the actual presentation. So prior to C++20, all C++ programs were undefined. That is a bold statement I'm making. And since C++20, things have changed. They're probably still undefined, but at least not for lifetime reasons. So a little bit of background, and then I'll explain what the problem was and how C++20 changes it, and how quantum mechanics factors into all of this. So first of all, the bit of background, construction versus assignment. The assignment operator never constructs objects. Except this is C++, so there's an exception. Sometimes when you have a direct union access, so like u.x, that can construct a member. But other than that, the assignment operator doesn't construct objects. Constructors construct objects. And this can kind of cause some problems, especially when you consider all of the C code where constructors didn't really exist. But we'll get to that in just a minute. So here we go. Basically, your code was busted prior to C++20. This code right here exhibits undefined behavior, mainly for the reason that I just mentioned, that when we call malloc, that gives us some storage, and we assign an int value into that storage, but there wasn't actually an int object there for us to assign into. But the problem is actually much broader than that, much more difficult. So consider this code, for instance. We construct an int. We use kind of this sort of like assignment looking syntax, but that is actually constructing an object even though it uses the equal sign. And then we do a reinterpret cast to a float, and we assign a value there. That's not allowed in any version of C++ or in C. That is called a strict aliasing violation. So if you want to read more about that, you can look online for strict aliasing C++ or strict aliasing C, and you'll see hundreds of pages of people reporting bugs against GCC's optimizer and them saying, nope, working as intended. So like this code here doesn't work. C++ community didn't want to make it work. But let's look back at that malloc example. Like this is code that we do want to make work just because, like in large part, just because we have to. Because if you ever use a C library, they do something like this. If they put it in a header, you're in trouble. Or if you have kind of C style C++ code, you'll write code like this. Basically, there's too much code doing this for the C++ community to say that it's undefined. So let's change this around a little bit and see like where the problems kind of run into. So here we have malloc size of int. What happens if we say size of float? In both cases, on most systems, that's actually 4. So malloc has no way of knowing what type it is that the storage is going to be. It accepts an integer for the size, and it returns a pointer. So what about this code? This code should probably be undefined, and in fact, it is in all versions of C++ and all versions of C. Again, it's a strict aliasing violation. It's fundamentally the same as this example here. Now, like I said, we want to make this work. We don't want to make this work. It's really complicated. Like, how do we do this? So just kind of keep that in mind. Here's another example. You might think, well, the problem there was that C interface where we were using malloc and it was returning a void star, and like, you shouldn't really be doing that. So maybe we have to do it for legacy reasons. But here's something using the standard library, the C++ standard library, allocator trait, standard allocator. And it turns out that this is actually undefined behavior in all versions of C++ prior to C++20. And the reason is anywhere where you say pointer +1. So for those of you unfamiliar with the allocator interface, when you call allocate, it's a typed interface. So it returns a pointer of the correct type, and it returns to you allocated storage that can hold a number of elements. So when we say allocate using the standard allocator with the number 2, that means allocate space for 2 ints. But the issue is we allocated space for 2 ints, but prior to C++20, we never actually allocated an array of 2 ints. So when you have the pointer to the beginning of the storage, it's not actually a pointer to an array yet, because we never constructed the array. It's just storage. There's no objects there. So when we say pointer +1, that's undefined behavior, because you can only index past the end of an array. So this was busted, but we fixed that in C++20. We said, okay, fine, allocator creates an array. But everyone's code was busted prior to C++20, because this code here even was undefined behavior. Like it looks reasonable. You take an integer and you reinterpret cast it to an unsigned char const star. So basically you want to look at the bytes of this integer. Maybe you're writing networking code or any sort of serialization where you need to stream the bytes somewhere would do something like this. And turns out this is undefined behavior. And in fact, this simpler version of the code is undefined behavior. This is all you need to make it undefined. And the reason is that the C++ standard and the C standard allowed you to do the reinterpret cast here and dereference and read and write, not write in this case because it's const, but if it weren't const, you could write. And that would be fine. But when you try to increment it, that's not allowed because there wasn't actually an array object there again, that you had a pointer to an unsigned char const, but you only had one of them. There wasn't actually an array backing that storage. So worst of all, this code here theoretically exhibited undefined behavior. It didn't by fiat. We basically just said it's the standard library, so there's no undefined behavior. But if you try to write your own vector by copy and pasting the code in the standard and just changing the name to not be reserved, it would be undefined. So, you know, everything about lifetime didn't really work. So how did C++20 fix it? It introduced the notion of implicit lifetime types. So implicit lifetime types are any type that has a trivial constructor and a trivial destructor. Any of its constructors, other than a copy and move, can be trivial. And that's sufficient to make it an implicit lifetime type. So an implicit lifetime type has its lifetime begin with the obvious C functions and also creation of array of bytes. And I'll list the full thing later, but like things like malloc. Anything that you would expect in C to kind of give you storage for stuff will give you actual objects and arrays that you can work with in C++. So where does quantum mechanics come into this? Let's go back to our old friend malloc. When we look at this example here, what's going on? We call malloc. An int has a trivial constructor and a trivial destructor, so it is an implicit lifetime type, which means that when we call malloc, there was an int that was implicitly created. Its lifetime was implicitly started. So after we call malloc, even though it returned a void pointer, it secretly actually has an integer alive in that storage whose lifetime has begun, and so we can just use the assignment operator and we can store the number 5 into that int. We can also, float is another implicit lifetime type. We can do this as well. We can store a floating point value into that storage created by malloc because a floating point lifetime started by malloc as well. But that brings us into some different quantum mechanic interpretations. So there's the Copenhagen interpretation, which, as I'm sure everyone familiar with quantum mechanics knows, was named for Johannes Strustrup because he was born in Denmark about 3 hours outside of Copenhagen, where the Copenhagen interpretation states that your program exists in a superposition of multiple possible states. So what that means is, like, if you're familiar with the Schrodinger's cat experiment, this is, you know, Schrodinger's malloc, where you call malloc and the memory returned is then a superposition of int and float, and basically every other type out there that can fit in the storage returned by malloc. And operations that observe the type collapse the wave function. So when you do that assignment operator, it went from being either int or float, so the cat was either alive or dead, and you observed it and you forced it to be one or the other. Now, unlike with traditional quantum mechanics, it's not just that you look at it and that makes it shows you what it was. Here, you do something and that forces it to be one or the other. So when we go back to our old friend malloc here, that equals 5 line causes the memory to become an int. Now, a competing interpretation is the many programs interpretation. Basically, functions like malloc cause decoherence, which means that it creates an infinite number of program states. In each of them, there's exactly one object alive. There's one for each possible set of types. Each one exists in its own universe with its own abstract machine, and undefined behavior destroys the abstract machine, possibly the universe with it, who knows. So this is actually the origin of the term program execution, because you run your program and the majority of them are destroyed or executed as they're running. So if no abstract machine remains, then your program's behavior is undefined. So what's the difference between these two interpretations? When we look at this invalid code here, we call malloc, and we have that second line that requires it to be an int and the third line that requires it to be a float. Now, in the Copenhagen interpretation, the first line has forced it to be an int, or that second line has forced it to be an int, and then the third line introduces undefined behavior, by violating the strict aliasing rule because it was an int and we tried to treat it as a float. Now, the many worlds interpretation says that there is one execution of the program in which it is an int, and there is one execution of the program in which it is a float. In the execution of the program in which it is an int, that float is undefined, and that execution is basically removed as a possible interpretation of our program. In the one where it's a float, the line where we treat it as an int is removed from the execution. Now, that means that both of those possible lifetimes are removed from the execution, and we're left with none, and thus our program has undefined behavior. So both interpretations will lead you to the same answers. They're just different ways of thinking about them. And the many programs interpretation seems more complicated at first, but as we'll see later, it actually simplifies understanding of how object lifetime in C++ works. So I mentioned earlier, I was going to go through what can start an object lifetime. There are the allocating functions, malloc, calloc, realloc, operator new, and the array form, and then a new function, aligned alloc in C++20. Also, creating an array of char, unsigned char, standard byte will create objects of these implicit lifetime types. They all start some unspecified set of lifetimes that are either proven or forced later on in the execution, depending on which interpretation of quantum mechanics you prefer. So as an example, this code is well defined in C++20. We create an array of bytes, and then we treat that array as an int. Creating the array has started the lifetime of an infinite set of objects that are 4 bytes or less and that have an alignment no stricter than int. And once we cast it to an int reference and assign the 5 to it, that's meaning that the only remaining interpretation of our program was that it was an int all along. And had we done this, it would have been a float all along. And so we can't have both of these two statements in a legal execution of our program. So what other function can start a lifetime? There's copying functions, memcopy and memmove. These maintain the existing types. So you can have storage and whatever types are in there. When you call memcopy on it to new storage, you create new objects that have the same type as the old objects. And then there's bitcast, where you specify which type you're trying to create. It maintains the representation, but creates a new type there. Similar with quantum mechanics, there's the no cloning theorem. C++ actually follows this. So here we have, we create 2 arrays, A and B, source and a destination. And the no cloning theorem basically states that it's impossible to create identical independent copies of a quantum system. And what we're seeing here is actually a manifestation of that. We do a memcopy from A to B, and then we treat A as an int. So it started out as this should say array of standard byte, not array of int. I'll have to fix that later. So assume that A and B are array of standard int 4. By treating the array A as an int, where the array is providing storage for it, that means that A must contain an int in it, which means it always contains an int in it, which means that B is entangled with A, and B must therefore contain an int. You cannot later treat B as a float, because that would violate the strict aliasing rule. There we go. And if we look at this example, when you do the statement int x equals 5, it's natural to ask what objects exist. So there's kind of the obvious one, int. There's also an array of 1 int. There is an array of 4 chars, array of 4 unsigned chars, and an array of 4 standard bytes. All of these objects exist simultaneously, and reading or writing through any of these will be reflected through all of the others. This basically explains why you are allowed to alias int and char. For instance, char, standard byte, and unsigned char can alias any other memory, because everything has some sort of storage. Basically, all 5 of these types are alive simultaneously. And if we create an array of standard bytes, then any object with a size and alignment that fits in A exists at that point, potentially. And then there's a C++23 feature called start lifetime as, which says whatever the object representation you have, keep it the same, but it is now this type T. So for instance, you can read bytes from a network, read it into an array, and then say, the stuff in here is a standard map, or it's a standard vector. And as long as it actually conforms to the requirements of the object representation, you now have an object of that type, and no other objects other than the various byte arrays. And start lifetime as also follows the no cloning theorem. In this case, it means that quantum mechanics, you can think of as implementing a destructive move. Once you call start lifetime as, the int object here no longer exists. You cannot access X and look at its value because there is no longer an int there. There is just a float there. And I think that is everything I have.
Well done. Well done. I like it. Man, I thought I was in the wrong presentation for the first couple slides. So
that was my goal.
Can you point us to where those rule changes were for C++20 that allow for there to be an implicit array at that location?
Yeah, I will send. Well, so when you say an implicit array at that location, so are
Well,
you
any of
talking
the implicit lifetime begin things, because I tried just now searching the standard for implicit lifetime, and I'm like, okay, I don't know what I'm actually searching for. Those
Paper
changes.
is 0593. Is that right, David?
That is
that the paper?
0593?
Yeah, I think so.
Yes, 0593 is the primary paper that made these changes.
Oh, funny, because
has-
Firefox auto completed it for me, which means I've already looked at it before.
Yeah, it's definitely a paper that the first time through, you don't necessarily get all of the implications of it. And it wasn't until this presentation kind of originated as a joke at the C++ committee meeting. I was like, this is kind of like quantum mechanics. And then I thought about it, I'm like, it's exactly like quantum mechanics.
So that was accepted in C++20 though?
Yes, everything except the start lifetime as.
Okay.
That didn't make it through library wording in time. So it
And that has not yet officially been accepted in C++23, or has it?
It has been accepted by the design groups, but its wording has not been approved to be merged into the standard.
Okay, sorry. That these are.
So it is not
important things
officially
to
in
what I
23.
teach. Okay.
I have a question. Can you help me understand why on some of your early slides you said the undefined behavior was when you increment the pointer?
Yes.
Not when you read the incremented pointer, but when you actually increment the pointer itself. Why is that undefined at that point?
Okay. So I guess technically I was somewhat imprecise there. You are allowed to increment it once because you can treat any object as an array of 1, and you can increment any pointer to a 1 past the end of the array. So you could not decrement it then, and you could not increment it again.
Okay,
I was recently made aware of this wording that was like, any other use of a pointer outside of these things is implementation defined behavior. And I said, what? Yeah. This, so sorry, go on.
I was going to say, Lenny asked a question in chat that I don't know if you saw.
I did not. Is it only a problem when you read? Why is it undefined if you only write different types? Okay, so the issue here is that the assignment operator requires an object to exist. And other than the union case, the assignment operator is insufficient to create an object. You would have to either call placement new or call standard construct at. Otherwise, you don't have an object to assign to yet. The assignment operator does not actually begin the lifetime of any object, regardless of its type. So it would be a problem for reads or writes.
And in the case of a union, if someone cared, you'd be looking for the rules on changing the active member of a union, I believe.
Yes, it has to specifically be I don't remember the wording for it, but it has to be like union.member.
Right.
And you can even say union.member.member.member equals 5, and that will recursively construct everything that you've mentioned in that union.
Okay.
As long as it's trivially something. I don't remember what the requirements are on that.
So prior to 20, was malloc usable in any form? Would you have to do a placement new into the memory returned by malloc? Was that possible?
That is,
Yeah, that would be what you would have had to do. And actually, like in C, this is all still undefined. Like their wording is kind of loose. So like if you look at it the right way, you can say maybe it's kind of defined. But like for the most part, like it's undefined, but everyone's like, yeah, but we all know what we mean.
Right.
And where a lot of this came out was like people started writing super optimizers, like things like CLE and super, where you give them like, these are the rules of C++, and they basically like evolve optimizations based on those. So if you have undefined behavior, they will break your code. And they're like, oh, but that's not, this is perfectly good code. Why are you breaking this? And it's like, oh, that's because it actually is all undefined. So there was a question in the chat, does start lifetime as call a constructor? It does not. Start lifetime as tells the compiler that this object's lifetime has begun. The object representation is already a legal representation for this object.
would it be fair to say it's like a legal reinterpret cast?
Yeah, but like it's kind of somewhere in between a reinterpret cast and a constructor, because the old objects that lived there no longer live.
Oh, okay.
So in fact, even if you had like a char star to the memory and you call start lifetime as, I believe that invalidates the pointer, even though it points to the same address, because it's a new object now that just happens to have the same object representation.
Okay.
What happens if what's there in the representation is not a valid member of the type? And
Then
in some sense, what does it mean to be like? I'm thinking of the case where you have an enum type that's underlying storage is, say, an int, but it only contains a couple of values in the enumerations. Is it considered valid? Is any value there considered valid, or is
it is?
I can't remember the exact details of this.
The enumerations have their own rules. Any value that's representable in the underlying stated type in the case of an enum struct is allowed. And in the case of a regular enum, it's like the number of bits required to represent all the possible values is what's allowed.
Man, who let the language lawyers in here?
Yeah, sorry. Anyhow, I think since the last speaker is Scott, and we have gotten derailed, and Scott has been doctor up to this point,
No worries.
I should take over and say, okay, Scott, why don't you go ahead and begin your lightning talk, and then we can discuss all of this when we're done here.
Yeah, you three can go geek out. All right, awesome. Yeah, so Docker and C++, why do we need that? And who am I? A lot of you know me, some of I've worked with you, but I thought it'd be fun to throw a slide up here, just to show who I am, and some slides and some bumper stickers and stuff like that. Currently, I have a drone company that have a bunch of college crews out flying for us and doing power line inspections, so that's fun. But what does that have to do with C++? Well, the only thing I'll say here is that I am looking for a new challenge. So if anybody knows of something and want to talk later, let's chat. Let's see. So why Docker and C++? Let's see. I have a bunch of potential reasons. Maybe some of these apply to you. Maybe you find some of these interesting that you hadn't thought of. One is because I think it's a nice way to have a clean, consistent development environment and allow you to be able to bounce around between different compilers, different versions, anything from Clang, GCC, picking the different versions. And then the other reason is not only in the first couple bullets, I'm talking about just building, right? I'm talking about building the binaries, but also deploying them. So you can deploy your C++ application without having to cross compile it, because basically you're bundling it with an operating system, or at least a light version of that you can then send on and not have to have a full VM system with it. So we'll talk about some of those too. I also like the fact that you can kind of version control your C++ dev environment. So for example, if you bundle up the compiler, the libraries, and everything else, publish it out to a company-wide repo, you can pull that repo down and use that as a consistent build environment. I know that in times past where I've built everything out and got it working and then try to deploy it somewhere, and all of a sudden things are broken because somebody else incremented some libraries or some compilers that I didn't know that the team had done. So this is a nice way to do that. You can deploy these C++ executables to AWS, Azure, GCP, because again, they're bundled, and these cloud providers provide a nice environment to support Docker containers. And then for polyglot programmers, like a lot of us are, having a knowledge of Docker, I think is nice, because there's a lot of other things that can be used with Docker. For example, in GitLab, the CI/CD pipelines, the task runners are actually Docker containers, and you specify the images and then script within that Docker container what you want your CI/CD pipeline to do. So if you have an understanding of the Docker itself, you'll understand how the CI/CD pipeline works. And there's a lot of CLI tools out there now that can be Dockerized and used universally between, for example, my Mac and my Linux and a Windows environment, which I don't claim to do a lot of I'm mostly in Mac and Linux based operating systems. But even the AWS CLI team has Dockerized their CLI to make it the easiest to install, because it's written in Python. And so having Python 2 or Python 3 and having that on your system and installing, and all the instructions basically go away. It goes down to a Docker pull, and you get the AWS CLI running. The only thing, of course, the caveat is you need to have Docker installed on your system. But I'm not going to cover installing Docker. There's a lot of great documentation exists out there. You do it once on your host system and you're good to go. And it's available for Windows, Linux, and Mac in a pretty consistent way. And like I said, these demos and the things I'm going to talk about are basically Linux and Mac. What I'll do is I'll do a quick review of kind of the structure, the architecture, the setup that I'm advocating that I'm suggesting you use. And then I'm going to provide 3 or 4 examples. One of them is compiling a C++ program for you to run natively on your host. The second one is compiling a C++ program that you would bundle and then you could distribute. And then the other one, for all of you Compiler Explorer lovers, I have Dockerized Compiler Explorer, and I've got a quick example of how I did that and how you can do the same. So the setup that I'm talking about here is basically I like using, and a lot of times, people who are not familiar with Docker and containers get confused about, well, is a VM, am I doing everything inside of the Docker container? Are my tools, like my VS Code, is all that stuff inside the container, or does it live outside? And I'm advocating that the bare metal has your Git repo. So the Git repo lives outside here, as well as your any of the other tools, your development tools you want to use, your editors and everything else, right? And then the Docker images are basically a union file system, which is also interesting that I'm not going to cover, but it provides a lot of speed and reusability within the host system, because it'll reuse whatever layers are consistent between the various things that you're building. So the container that I'm showing here is, the container is the actual instantiation in memory. And what I advocate is that you bind mount your source code into the container in most cases, especially during development. And then what's happening is the container itself is acting as your build environment. So it will have all the libraries, your static libraries that you can then statically link to create the executable. And the executable is then, in this first case that I'm going to show you, is stored back out on the bare metal. In the second example, I'm going to show you where I bundle it inside the Docker image. It would live within a Docker image that you will then not instantiate, but The Docker image is, think of it as a template. So the template is when you run the Docker image, it becomes a container, and you can have multiple containers running. So think of this as the class definition, and this is the instantiation of it from a C++ kind of perspective. So, okay, so let's do a little demo real quick with a simple hello world. So first of all, let me introduce Docker Hub. If you haven't heard of that, Docker Hub has several images that the community has shared. And so one of those, as an example, is a GCC image. So you don't have to have GCC installed on your bare metal machine. You don't have to have a specific instance installed. There's various versions that are installed or that are various images that are available that are different flavors of the GCC compiler. And within those Docker Hub notes, like if you just were to scroll down here, you would see how to, one way to run it is to simply issue this command. And the command I can go through and I'll talk a little bit about it, but about what it's doing. But the essential part of it is the last part, where it's basically just saying, hey, within the container, do a GCC, create an output file called myapp, and myapp.c is your input file. So what this is doing is mapping and doing a binding. It's doing a binding of the source code into the container so that the GCC compiler on the inside of the container can see it and compile it and then write it back out. Oh, and there's also just recently on Tuesday, AWS ECR Public was announced, which is a competitor to Docker Hub now, where more public repositories are popping up and made available. So let's see. So how do we do this? So here's our simple hello CPP source code. Here's the command that we talked about, right? So it's let me just walk through this real quick just to make it less daunting. So all we're doing is we're saying Docker run, that's the command. --rm is saying to remove the container once I'm done compiling. I don't want it sticking around on my host machine because it would live there with the ability to restart it in its execution state that it was in. The -v is just taking, it's a volume, it's a bind mount. It's saying, hey, take my current directory and mount it as part of /project inside the container, and then make the working directory for the GCC, the G++ command that I'm going to issue, make that working directory the /project where I just copied my code and copied my environment into. And I'm saying, give me the GCC 10.2 compiler, and then run this command within that. Or if I had a make file, I could do the same thing, right? The only thing that's really important is these last couple of commands out here. And so what you'll see me later do is I can actually take this code right here and I can make an alias out of that very simply. Well, actually, it'd be more along the lines of this. Yeah, and actually I see no, that would actually work. This is where I would have as an alias. And then I could just type, like if I made an alias of GPP, I could say GPP and then give it these options and it would do the same thing as typing G++ if I had that on my host machine. So when I get done with that, I can look and I can say, hey, this command actually, I have an executable, and on the host machine, on my Linux machine in this case, that would compile. Now, if I did this on my Mac, there's some subtleties here, right? The subtlety is that the GCC compiler, the image is built with an Ubuntu base image. And so it's building it with that as a focus. And so it wouldn't have, it wouldn't have that cross compiling for the Mac. So there's some subtleties about when you're building specifically for the host that you want to run on, you want to make sure that you have all the right cross compilers if you do need to do that. But in this case, because I'm demonstrating here that I'm using the GCC on a Linux machine, and then I can run the executable without any issues. So let's see. Within the Docker Hub, you can see that there's other tags that are available. For example, if I wanted to grab the 6.5 compiler, the only thing I would need to do to change from GCC 10.2 to 6.5 and just to recompile this would just change that tag right there. In essence, it would download the new image for the version of 6.5 that's been tagged that way by the official GNU team. And it would, again, run as expected, right? Or at least it should. Here's the alias I was talking about you could give as an option. And I'm just trying to show different examples to show kind of like a workflow of what's possible with the Docker containers. Let's see, you can also build your own environment. The LLVM Clang team talks about how to do that here. They've got some really good documentation. So take a look at that. Again, I kind of look at it as environment as code, or sometimes, infrastructure as code is a buzzword now too. And something, if your company has some proprietary flags or whatever, it's easy to set that up within an image that you can then post on your company's own proprietary Docker repo, and the team could then have that pretty easily and consistently. So this demo will talk about run anywhere that Docker's installed. Again, I get that is the one caveat, but it does avoid the cross compilation, and you can deploy it to the cloud. What I'm going to show here is a multi-stage build. So the first build is just the builder stage. It has everything that's needed to build the executable. And then what I'm doing, I'll demonstrate, is it's copied from the build stage into what we call an executable stage, which is that build stage then gets discarded, and the executable stage has only the final executable. And why is that important? Because it's a much smaller Docker image that you can distribute, and it's not that much more work. So the Docker file, let me just walk through this real quick. So the way this works is we have from GCC. I'm naming this stage as builder. So I'm grabbing the 10.2. I know that it's based on an Ubuntu image, but I can show you that in specifically how you could figure that out if you didn't know it. I'm setting the working directory to /project. I'm copying my code from the host machine into /project. Again, just telling it, hey, run G++ with an output of hello, and compiling my source code. And then once it's done, it's this indication I've got a from bundle stage. I got a from line that indicates that it's the next stage. So I'm taking, in this case, an Ubuntu, and Ubuntu used to be a couple hundred megabytes, but they've reduced it down to about 70 now. So it's a lot smaller. And then I'm just taking, hey, create a work directory, copy what was in the builder stage up here, specifically copy the hello executable and that I named here, and put it into this working directory app. And then the final thing is run the command .hello. So in all of that, to build it, I simply issue that command again to build the Docker image. I then run the image and tell it to remove the container once it's done. And of course, it runs as expected. But the nice thing about seeing, we can kind of compare some of these and why the build stages and having multi-stage is important. So this down here is the image. If I were to take that simple small hello world and leave it within the GCC's container image, it's almost 1.2 gigabytes. So that's huge, right? So you don't want to distribute something like that. So what I showed you was using the Ubuntu image, and it's still pretty hefty compared to the fact that the G++, and I didn't compile it statically, right? So I understand that what I was showing before is only like 17 kilobytes. And so comparing that to 79 megabytes still seems large. But again, what you're getting is the ability to run this on multiple machines, deploy it to the cloud, and that kind of stuff. But there is also the ability to use an Alpine image, which is a little bit more work to configure. but it gets it down to 12.6 meg. So that trying to show you the relative size of how big some of these images can be, or small. Let's see. So now, Dockerized Compiler Explorer. Why? Well, running locally might be nice for some teams. You might want to figure out how to contribute to the project. And so having it locally built up and understanding how it works within your Docker container would also be a nice thing to have. You can also customize, if you had it built in locally, you could customize it for your own compilers and options. If you're in a disconnected environment on a plane, maybe, when Jason's flying back and forth between Europe, he doesn't want to pay the Wi-Fi prices. If he has the Docker image installed, he could use Compiler Explorer to his heart's content. Let's see. Also, company proprietary concerns. I know that there are some companies that are concerned about copying and pasting their code into Compiler Explorer, and so have restricted or limited them from that. So having their own Dockerized version might be nice. And there's also government networks that I've worked on before that would also prevent that. So how do you do it? So these are the simple steps to get it to work. So you just git clone the Compiler Explorer repo. I am using a node image, which is based also on an Ubuntu. I create a working directory for the Compiler Explorer. I set it to dev environment, copy the package.json. So if you don't know, Compiler Explorer is written in Node. And so the package.json is kind of the piece that tells the node, the npm install down here, what packages it depends on. So it can pull them down and install them. This is just a step to remove any code that might be already there. Copy now the rest of all of the code into our Compiler Explorer directory. Then we run this Webpack CLI, and it builds it up. And then the final command is to execute the node with these options here with the app.js. And if you do all that with the compiler, with that Docker file, you can then build the image. And I haven't talked about Docker Compose just because this is going long and I want to just keep it simple. But then to run it, all you would do is do Docker run. And because of a peculiarity with Node, you want to do a --init with the dash port. So you're opening and you're publishing ports from the outside, from your host machine to the inside container, and telling it which image to run. And by doing that, you can then go to your local host and hit port 10240 and have your own Docker compiler Explorer running locally on your own machine. So there's a lot of other things that you can do here. The instance that I showed, the Docker file, only gets you the default G++, I think it's a 6 compiler in this case, but adding others is just nothing more than adding a couple additional commands to this Docker file. So, I hope that helps maybe understand or clarify maybe how you might be able to use C++ and Docker to build containers, share your C++ code with others from a Linux to a Mac to a Windows environment, and how Dockerizing just applications in general is not as daunting, I think, as maybe a lot of people thought if you haven't used it before. So that's my presentation.
Thank you, Scott.
Yeah, you bet.
I guess if anyone has a quick questions for Scott, and then I'll hit the stop recording button in a moment. I actually am curious, if I were to actually use Docker to invoke GCC for each individual CVP file, what kind of extra overhead does that add?
For each individual, so the overhead is not bad at all. It's I mean, how do you explain it? So the Docker containers run really close to native performance, right? It's not like through the VM per se. I will say running it on Linux is much more performant than running it on like a Mac, because Docker is in fact running, when you install Docker desktop on a Mac or Windows, it is a VM that's running because it has to emulate the Linux functionality of C groups and what the heck's the other thing? I'm drawing a blank right now, but so there are some things that aren't native in those other operating systems yet to allow the full functionality without having the VM. But if you're on a Linux box, it, like I do most of my work on, it's really performant. It's really fast.